Okay, so so does anyone remember what the ideal gas law is? Can someone tell me what the ideal gas law is? Great, PV equals nRT. This is definitely an equation you should memorize because it's that important. So PV equals nRT. And does anyone remember the value of R? Great. So 0.08206 liter atmospheres per mole Kelvin. Okay? So we have 4 moles of gas at a pressure of 5.6 atmospheres and a volume of 12 liters. What is the temperature? So we should rearrange this equation to get T equals PV over NR. And then you can just, and then this is not too difficult to solve, right? Okay. And then this is basically all of the other, it's the same thing for all the other questions. Just remember that this is in Celsius, so you need to convert to kelvins first. So does everyone remember how to convert Celsius to Kelvin? Right? Great. So you just, yeah, exactly. You just need to add 273. Okay. So now with that out of the way, I think we can start the lesson now. So today we're going to be talking about liquids and intermolecular forces. And if we have extra time, we can also cover some stuff about solids. Okay. So first, what is a liquid? Okay. So liquid is one of the 4 fundamental states of matter. So the other states, does anyone remember the other states of matter? So we have gases, which we already covered, and we have solids and plasma. Okay. So liquids have some interesting properties in that they are nearly incompressible. So unlike gases, which can be easily compressed, like their volume is not fixed, liquids have an essentially fixed volume. Okay. And in a liquid, the molecules flow freely around each other, but they also stick together with significant forces of attraction, which is why, unlike in a gas where all the particles can fly around and they don't really attract each other, in liquids, the molecules do attract each other, which is why liquids hold together. And liquids have much higher density than gases. So if you remember from the last lecture, gases have very, very low densities, like we calculated. But most liquids, so for example, most organic liquids usually have a density of around 1 kilogram per liter. And some liquids can get even as dense as 20 kilograms per liter. And most solids also have very high densities compared to gases. Okay. So, yeah, wait. So solids. In solids, we start to have more significant attractive forces between molecules or atoms. So this means that solids are incompressible and they have a rigid shape, right? Okay. So I want to talk about intermolecular forces. So these are the forces that hold molecules together, okay? Or atoms together. So for example, in a cup of water, why don't all the water molecules like fly off into space? Why do the water molecules stick together? It's because of these intermolecular forces, or IMFs, okay? So intermolecular forces are between 2 different molecules, and intramolecular forces are between 2 of this in the same molecule, in one molecule. My stylus is missing. Okay. So inter, so these are intermolecular forces because they're between different molecules, okay? So if we remember to the lecture about covalent Lewis structures and covalent bonds, we saw that atoms and molecules share their electrons. So they share these electrons and we get this cloud of electrons that forms the molecule. However, not all electrons are shared equally. They're not all shared equally because remember that the more electronegative elements really want electrons. They really like having electrons. So they're more willing to attract electrons, okay? And the more electropositive elements are more willing to give them up. So your electronegative elements will have more electrons and the electropositive elements have a lower amount of electrons. So what we would call electron density. Okay? So electrons, are charged particles. Electrons have a negative charge. So this means that an unbalanced distribution of electrons causes these partial negative and partial positive charges. Okay? So you have one end of the molecule that has a positive charge and one end of the molecule that has a negative charge, almost like a bar magnet. A bar magnet has a north side and a south side, right? So we have a positive side and a negative side. So just like the north side of a magnet will attract the south side of another magnet, the positive charge on one end of the molecule will attract a negative charge on the other end of the molecule, right? And by the way, this is also called a dipole. So this is why we call this is why these are called dipole forces. So it's because the molecule has two poles, right? It has a positive end and a negative end. So the molecule acts as a dipole, and these dipoles attract each other, right? So as you can see in the schematic, we have what's called an interhalogen. So we have iodine bonded to chlorine, and the lone pairs are not drawn, but that's fine. So the positive charge on iodine, by the way, see this delta sign? That means that it's not a whole positive charge or a whole negative charge. So this delta means that is a partial positive charge. This is a partial negative charge. So it's not the whole charge of an electron. So if we count the charge of an electron as one charge, then this is like less than that. So these charges are not super significant. So they're nothing like the charges we talk about like in ions, like our 1+ ions or 2+ ions or 3+ ions. So we have these relatively small charges. So you can see the negative charge on the chlorine attracts the positive charge on the iodine, and same here, right? And you might imagine that this positive charge, you might think that this positive charge would also repel this positive charge, right? But this charge is farther away, right? So because it's farther away, the force of repulsion is not as strong as the force of attraction, okay? So looking at this picture, can someone tell me whether chlorine or iodine is more electronegative? So is chlorine is Cl, or iodine, which one is more electronegative? Right, chlorine, because chlorine has a negative charge, which means it's attracting the electrons more, which would indicate a more electronegative element. So here we can see this picture shows a sort of distribution of electrons. So this is the shape of what's called electron cloud. So you can see for this nonpolar covalent bond, so it's nonpolar, that means that all of the electrons are very evenly distributed. So there's no difference in electronegativity. When we have a moderate difference in electronegativity, then we have this what's called a polar covalent bond, so our two poles. And so you can see that more electrons are focused around this atom, and there are less electrons here, okay? Here we have, and then finally, at the extreme end, we have the ionic bond. So in the ionic bond, we have a very large difference in electronegativities. For example, a non-metal and a metal, so like chlorine and sodium. And so the chlorine would take all of the electrons, and the sodium would give up a whole electron. So so more of the electrons are concentrated around the anion, right? Okay. Now, so depending on the shape of the molecule, even if the bond itself has a partial positive and partial negative charge, that doesn't mean the whole molecule will exhibit these partial positives and partial negatives, right? For example, carbon tetrachloride, CCl4, so also known as carbon tet. So it's used as a solvent in the cleaning industry. So let me draw the Lewis structure. Right, okay. Can someone tell me what the steric number is? Does if anyone remembers back to the talk about molecular geometry, does anyone know what the steric number here is? Around carbon. Great, 4. So we have 4 bonds and no lone pairs. So this is a steric number of 4. So can someone remember what shape a steric number of 4 would cause? What shape should we have? Great, it should be a tetrahedron. So all of these chlorines will repel each other. So to minimize the repulsive forces, they will arrange themselves in a tetrahedron, which I will try to draw. And I've omitted the lone pairs for clarity, just to make the picture a little neater. Okay. So can someone tell me what the more electronegative element is? Is it carbon or chlorine? So you might want to look at a periodic table. Great, it's chlorine, because the more electronegative elements will be at the upper right corner. So the upper right area of the periodic table, so like near fluorine, fluorine is the most electronegative element. So those elements will be more electronegative. And as a side note, even though the noble gases, so the last column of the periodic table, so those are the rightmost, but they don't really have assigned electronegativities because they're basically unreactive. Okay, so the chlorine they all get a partial minus, and carbon gets a partial plus. So we can draw our dipoles. So we usually draw it like this. So the arrowhead is the negative side, and we have a cross at the positive side. Right? Okay. So as you can see, all of these individual dipoles cancel each other out because they're all facing in opposite directions. So overall, carbon tetrachloride does not have a dipole. So we don't really see significant dipole forces in carbon tetrachloride. So as another example, let's look at NH3 ammonia. So can someone tell me the steric number of ammonia? So ammonia. Right, so 4, we have 3 bonds and 1 lone pair. 3 plus 1 is 4. So we'll form a tetrahedron. and we have our lone pair here. So this means the atoms are arranged in a trigonal pyramid. Now, which element is more electronegative, hydrogen or nitrogen? Right, nitrogen. So this gets a partial minus, and these all got partial pluses. And so our dipoles face this way. Oh, I can do that in a different color, actually. So, okay, so we have our dipoles, what are called bond dipoles, I guess you would call them that. And then notice how all of these point in this direction, in that direction, right? So even though some of them point in that direction and that direction, that cancels out. So the net effect is one dipole moving in this direction, okay? So the same goes for H2O, which I'll just do quickly. So overall, we get that dipole. Okay. Okay. Now I want to talk about London forces, because remember when we looked at CCl4, it didn't have a net dipole, and many other molecules also don't have dipoles. So, for example, carbon and hydrogen have very similar electronegativities. So compounds that are made solely of carbon and hydrogen, so what are called the pure hydrocarbons, don't exhibit dipole forces. So for example, gasoline is an example. Gasoline. However, gasoline still sticks together. The molecules in gasoline will still stick together. And at a low enough temperature, anything can become a liquid, right, or a solid. So these molecules still need to attract each other somehow. So this force of attraction is called London forces. So non-polar molecules will still attract each other. And basically the reason why this is because our electrons are always going to be moving. So the electrons in the molecule or atom are going to be in continuous random motion, okay? So we have an unknown distribution of electrons in the atom. It's random. So statistically, at any random time, just by sheer luck, we might have electrons that happen to be more concentrated on one side of the atom or molecule. So this creates a concentration of electrons at one end and a relative dearth of electrons on the other end. So we have a positive charged and a negatively charged side. And this is what we would call an instantaneous dipole, because it just appears for an instant. However, what happens is that this instantaneous dipole will also disturb the electron clouds of another atom. So for example, in helium, we have our 2 electrons, and they're flying around randomly. So at this one moment in time, we have a negative charge here. We have more electrons on this side, which creates a negative charge here and a positively charged here. And now we have another helium atom with its electrons flying around. And then those electrons can sense this positive charge. So they get attracted to this positive charge. So more electrons start moving onto this side of the atom. And then this creates another dipole, what's called an induced dipole. But as you might imagine, these dipoles are not permanent, and these instantaneous dipoles are quite random. So this means that London forces are relatively weak compared to the other IMFs. So here I have this nice picture of liquid helium. So liquid helium, so helium gas turns to a liquid at around 4 Kelvin. So you can imagine how cold that is. That's negative 269 degrees Celsius. so very, very cold. Um, and at that point, liquid helium, it crosses what's called the lambda point. So it starts to exhibit superfluidity. So basically, you know how water or like maple syrup or something is very like thick. So it's what we would call viscous. It has some viscosity. It sticks to stuff and doesn't flow freely. Well, at past the lambda point, so helium loses all viscosity, so it becomes a superfluid, and it frees completely completely freely. So it does not exhibit like viscosity or friction or anything like that. So what can happen is that the helium will actually climb out of the walls of a container, right? So kind of amazing. It can just climb out of the walls of a container because it doesn't exhibit any viscosity. And if you were to swirl a cup of like liquid helium, it would just keep on swirling. It wouldn't stop. Okay? And the main application of liquid helium as it's a cryogenic coolant. So, you know, in like your MRI machines and stuff like that, you have to keep the magnets super cool. So you use liquid helium. Okay. So, as you might imagine, if you have more electrons, a larger electron cloud, then your electrons are easier to move around, right? There's just more of them. So you get stronger London forces. So larger molecules have stronger London forces. And this is called polarizability. So if you look at your periodic table, so an atom like iodine, so iodine, has a very large electron cloud. So iodine is quite polarizable, and it has very strong London forces. Okay. So, however, fluorine, F, is a much smaller atom. It has less electrons, and it's less polarizable. So in fluorine, we have very weak London forces. So F2 is a gas, but I2 is a solid. So you can see the effect of this differing strength in London forces. And one point I want to emphasize is that all compounds have London forces. All compounds, all atoms, everything has electrons, so they all have London forces. Although sometimes they're very weak. So like in helium, we have very, very weak London forces. Okay, now there's one final IMF I want to talk about, which is hydrogen bonding. So hydrogen bonding is by far the strongest intermolecular force. So basically, if we have a hydrogen bonded to a very, very electronegative element like oxygen, this hydrogen will be very electron deficient. So it will have a very large partial positive charge. So for example, this hydrogen here. So what are these electronegative elements? So there's three of them that you really need to consider. So fluorine, oxygen, and nitrogen. So F, O, and N, and N. And okay, so if you have a hydrogen bonded to any of those elements, you have a potential for hydrogen bonding. Okay. So, okay. So these electron deficient hydrogen atoms will interact with the lone pairs on other electronegative elements. So we have a lone pair on this oxygen. So it will interact with this hydrogen molecule in what's called a hydrogen bond, where this hydrogen acts as the H bond donor, the hydrogen bond donor, and this lone pair acts as the hydrogen bond acceptor. Okay? So, so you might not see this in AP chemistry, but if you look at molecular orbital theory, you'll see that hydrogen bonding has some partial covalent properties. for example, the bifluoride ion, HF2 minus, which is a very, very interesting structure. So it looks like this. That should be a fluorine. This. Right? So this is very strange because we have this hydrogen with 2 bonds. So it's a little special. So that's one example of a very, very strong hydrogen bond. So somewhat abnormally strong. Okay? So hydrogen bonding is a little complex and it has some strange properties. For example, this hydrogen will only really bond to one other lone pair. So, for example, also it's linear. The structure tends to be linear. And each lone pair only really interacts with one hydrogen atom at a time. So all of these are similar to covalent properties. So this is why I say they have partial covalent properties. Okay. Now look at, these are the boiling points of the different atoms. So as you increase, if your substance has a higher boiling point, do you think it will have stronger or weaker IMFs? Right, stronger. Because if you have a very high boiling point, that means your atoms and molecules have to move very, very fast to disassociate from each other, to separate from each other. So you have what are called homologous series. So HOMOLOGOUS, if you're wondering. So as you can see, we keep the hydrogens all the same, but we change the element of the central, the identity of the central atom. So oxygen, sulfur, selenium, tellurium. And I want you to notice that these are all in the same column of the periodic table. So all in the same column, so column 16. So oxygen, sulfur, selenium, tellurium. And we have fluorine, chlorine, bromine, iodine, and nitrogen, phosphorus, arsenic, antimony, and bismuth. So polonium and astatine are both very, very radioactive, so they are not included in the graph because they're too dangerous. Okay. So, okay. So as you can see, because we have the very strong hydrogen bonding, these have abnormally high boiling points. Right. So we have electronegative elements, so oxygen, fluorine, and nitrogen, and they have lone pairs. So these are perfect conditions for hydrogen bonding. Okay. So now we have a significant drop here because these elements are not highly electronegative. So they're not as highly electronegative as oxygen, fluorine, and nitrogen. So we have sulfur, chlorine, and phosphorus instead. But then we have an interesting trend in which the boiling points actually start to increase. Now, can someone tell me what IMFs are getting stronger that cause this increase? So remember our 3 IMFs. We have dipole forces, we have London forces, and we have hydrogen bonding. So which one of those IMFs explains this trend? So can you explain why you say it's London forces? You can unmute your mic and just explain why you think it's London forces. Or type it. Great, exactly. So as you go down the periodic table, we start to see larger and larger atoms with more and more electrons. So the number of electrons gets larger, so we start to see significant increases in London forces. So you might be asking about dipole forces. Well, as we go down the periodic table, as we go in this direction, the atoms start to become less electronegative. So we start to see actually weaker dipoles. So the dipole forces are actually somewhat diminishing. You might argue that they're a little diminishing. It's a little complicated because the bond lengths also change, but I wouldn't worry about, but you can say like the dipole forces do not increase significantly. The real change here is the strength of London forces. Okay, so let's do another example. Let's do an interesting example. Okay. So I want you to consider the series. So methane, silane, germane, I think that's what it's called, stannane, and plumbane. So CH4, SiH4, GeH4, SnH4, and PbH4. So the structure is this, right? And where X is one of these elements. So does everyone see why the structures are all the same? Right, because they're all they're the same column of the periodic table. They're kind of similar, so we get similar compounds. So, what do you think if I were to graph the boiling points, what do you think the graph would look like? So do you think they will increase? Will they decrease and increase? What do you think? What should the graph look like? Right. So we don't see any significant dipole forces, right? Because all of the dipoles cancel out anyway, because they're all in opposite directions. Furthermore, we don't see any hydrogen bonding, since none of these are super electronegative elements, and there's no lone pairs, right? We don't have any hydrogen bond acceptors. So the only thing that's affecting the boiling points are the London forces. And since we're going down the periodic table, we're adding more electrons. So we have increases in London forces. So we should see something that looks like this, right? Okay. So I want you to do these problems. So I want you to identify, so your job, what you need to do is you need to draw Lewis structures for these molecules. So draw their structures and tell me what forces are present in them. So are there dipole forces, London forces, hydrogen bonding, or a mix of both? Okay? Or a mix of all of them. So I'll give you 10. So I think now would be a good time to go over the answers for this problem. So first, okay. So I think the first step would be to draw the structure of all of these molecules. So what do we have here? We have chlorine, ammonia, carbon tetrabromide, methanol, and dimethyl ether, okay? So if you want to know their names, that's what they are. So First, we have chlorine, dichlorine. Two is ammonia. Three is carbon tetrabromide. Four is methanol. And finally, we have dimethyl ether. Okay, so let's start with chlorine. So does anyone, okay, so remember all molecules have London forces. So I'm going to write the types here. So from weak to strong. So all molecules have London forces. So we know that chlorine has them, right? Now, do you think chlorine gas has a dipole moment? Just yes or no. Do you think we have a dipole moment? Are there going to be partial positive and partial negative charges? So remember, a dipole moment comes from a difference in electronegativities. So do we have a difference in electronegativities here? So for chlorine, they're the same atom, right? Exactly. So they're the same atom. So if they're the same atom, how can we have a difference in electronegativity? So no, we do not have a dipole moment. Do we have hydrogen bonding? What do you think? Nope. Right. We don't even have hydrogen atoms here, so we can't have hydrogen bonding. Okay. Ammonia. So all molecules have London forces. What about dipole forces? So do we have a more electronegative element? More electronegative element. Right. Yes. Because the nitrogen is more electronegative than the hydrogen. And then if we look at the structure, we have an overall dipole. So yes, we have dipole forces. What about hydrogen bonding? Do we have hydrogen bonding here? So do we have hydrogen bonding in ammonia? NH3. Right, yes. Because we have a highly electronegative element. So those are N, O, and F. We have a highly electronegative element. And we have a hydrogen bonded to that highly electronegative element. And we have a lone pair to act as an acceptor. Great. Now, what about carbon tetrabromide? We have London forces, right? What about dipole forces? Do we have an overall dipole? Okay. So can you tell me why you think there's an overall dipole? So carbon is in the middle, right? Yeah, that's true. And carbon is less Carbon is a little less electronegative than bromine, although the difference probably is not too significant. I can't remember the numbers off the top of my head, but there might be there's somewhat of a difference. However, all the negative charges point away from each other, so all of the dipoles point away from each other, and actually they're pointing away from each other in such an orientation that they all cancel each other out. Okay, so they all cancel each other out, so we don't have an overall dipole. What about an H bond? Do we have hydrogen bonding here? So I don't think so, since there aren't any hydrogens. So, okay, methanol. So it has London forces, we know that. What about a dipole moment? Do you think it has a dipole moment? Okay. This one. So we have oxygen is more electronegative than carbon and hydrogen. So you have a partial minus, partial plus, partial plus. So we have an overall dipole in that direction. And we have hydrogen. We have a hydrogen atom, and it is bonded to a highly electronegative element. Plus, we have some lone pairs. So we do, in fact, have hydrogen bonding. And the last one is methanol. I mean dimethyl ether. So we do have London forces. I did draw it in a kind of a funny way. So here's the structure. So this is a more accurate representation of the structure. So we have partial positives and a partial negative. So we have an overall dipole in that direction. So we have dipole moment. We do have dipole forces. Do we have hydrogen bonds though? So do we see hydrogen bonding in this molecule? No? Can you explain why? Okay, well, there are no lone pairs on carbon, right? But carbon is not going to act as a hydrogen bond acceptor, so we don't need to worry about that, right? What we do need to worry about is the two requirements for hydrogen bonding. The two requirements. So I will write them down for extra clarity. So one, hydrogen, we have a hydrogen atom bonded to nitrogen, oxygen, or fluorine. Two, we have lone pairs on nitrogen, oxygen, or fluorine. So we do satisfy this requirement. We do have two lone pairs. However, we do not satisfy this requirement because there's no hydrogen atom bonded to this oxygen atom. So we do not have hydrogen bonding. So although dimethyl ether is a bigger molecule and it has stronger London forces than methanol, methanol is a liquid and dimethyl ether is a gas. Okay. Let's check the time. So I think we can take a 10-minute break now. So can you come back at 8:03? So have a break until 8:03.